Um, so there's four basic gas laws. And on Wednesday, we're going to do an experiment to see how they're all related. Because you can probably tell just by some of the experiments we did last week, and just looking at the values in the equations for the different laws, you see they're kind of related because there's pressure, there's volume, there's temperature, and then there's the number of moles. Those are like basically the four things that we're going to vary, and change any one of them, and you're going to see differences in all the others. And so what we do in this particular experiment is to try and hold one or two things constant, like we have a constant amount of gas in a constant volume. And then we change the temperature and see what that effect that has on the pressure. Or we have a constant pressure and a constant amount of gas. And we see what changes the temperature has on the volume. Basically, each one of these things, they're all interrelated. And so if we want to see the effect of just one of those things on one other things, the other two have to remain constant. And so we'll sort of go over how to do that today. The other thing we're going to learn about in class is basically why these things are connected. And they're connected with something that we call, let me get something to write on here. KMT, or the the kinetic theory of how gases, how the movement of gases are related to all of this stuff. And so remember that when we talked about the pressure, what does pressure mean? And pressure was raised when the molecules of gas started hitting the sides of the container more frequently. And so they hit the sides of the container more frequently when a couple of different things happen. One, just put more gas in. And that made sense because the more gas you had, the more times it's going to come in contact with the container. The other thing that changed the pressure of the gas is when we raised the temperature. When you raise the temperature, the molecules start moving faster. And as they move faster, they're going to hit the sides of the container more frequently. So the pressure will go up. And then the other thing that raised the pressure is when we lowered the volume. So we had a large volume. There was much farther for each of those gas molecules to go before they came in contact with the container. When we squished the container so that it was smaller, the molecules had less distance to go before they came in contact with the container, and so the pressure went up. And so it's actually the movement of molecules that is responsible for all of these behaviors. And also, that helped explain that when we measure temperature, how do we measure temperature when we talk about gas? Which scale do we use when we're talking about temperature when we're dealing with gases?
Kelvin?
Mm-hmm. Why is it that we use Kelvin? Why not just use, Fahrenheit or Celsius or something else? Try and relate it back to the movements of molecules. Why would Kelvin be the best way to deal with it? What's unique about Kelvin?
Was it that there's no negative?
That's the perfect reason why. Basically, two reasons, but that's one of the main reasons. So, yeah, there's no negative temperature, and so when you're doing calculations You can't have negatives in there because there's no such thing as negative pressure or negative volume or negative numbers of moles. Those are all positive numbers. They're either 0 or they're a positive number. There's no negatives. And so having Kelvin as a scale in these calculations helps because there's no negative temperatures. What's unique about 0 Kelvin? When we get to 0 Kelvin, what happens to the movements of molecules?
Nothing. Like there's nothing happening.
Yeah, they stop. They stop moving completely. So absolute 0, all atoms, all molecules basically stop moving. And so if gases stop moving, they no longer have any pressure because it takes the movement of gases hitting the side of the container to get any pressure. And so if we want to calculate pressure, we want to start at where there's no pressure. And that starts, helpfully, at 0 Kelvin. So at 0 Kelvin, there would be 0 atmospheres of pressure, no matter what size your container was, because those molecules will not be moving to hit the sides of the container. So let's look at the laws we're going to be doing today. So first we were going to do Boyle's law. So Boyle's law is right here. And basically what that tells us is sort of what I mentioned before. There's a relationship between volume and pressure. And when we have that piston that we're going to be dealing with, so here's a piston pushing down. If we change the volume that gases are in, let's say we'll put some molecules in there. Oop, erase that one. So we put some molecules in there, and they're going to be hitting the sides of the container at some particular frequency because of the temperature. And so we measure the volume. We measure the volume. Damn it, what's going on here? There we go. So we measure the volume, 1, and the pressure, 1. So whatever the conditions were initially. So 1 would be whatever they were initially. And then let's change them. And we push that down a little bit further. So now it's like half the volume that it was before. So the volume is now 1/2 of what it was before. What's going to be the change to the pressure? Now that I've reduced the volume, we haven't sped up the movements of any of the molecules, but they're in half the volume they were before. What's going to be the change in the pressure?
Half of the pressure?
So think, if you change the volume, if the pressure is related to how frequently gas molecules come in contact with the size of the container, if the container is now half the size, is it going to come into contact more frequently with the size of the container or less frequently?
More frequently.
More frequently, right. And so what Boyle noticed doing experiments just like this, actually, with a piston just changing in a seal, a gas-tight seal on the piston, and just basically measured the pressures as he changed the volume, and noticed that when the volume was halved, the pressure went up by 2. So you had V1 was divided by 2, but then P1 increased by 2. So would we say that they're directly related or that they're inversely related?
Inversely.
Inversely, right. As one goes up, the other one goes down. And you can sort of see this when we look at this particular expression, because if we multiply V1 times 1/2, which is this over here, so we take 1/2 in the denominator and we take or 2 in the denominator and 2 in the numerator, you see that the volumes and the pressures now equal each other. And so what we can say is that the initial volume times the initial pressure will be equal to the new volume times the new pressure. So in other words, if the volume goes up, the pressure will go down at exactly the same way. And if the volume goes down, the pressure goes up. So anytime you multiply the volume and the pressure together, we're going to get the same thing. And that's basically Boyle's law. So anytime you see two things multiplied together, that means they're inversely related. Because if they were directly related, if the volume went up and the pressure went up at the same time, then we couldn't multiply them because there's no way they would be equal. When we changed the volume, that went up and the pressure went up, then our new volume, our new pressure would both be greater when we multiplied them. So we can't. So they're inversely related when we multiply them together. Now, when you look at Charles's law, it's basically the opposite. So what happens here? So in this particular instance, with Charles's law, what Charles noticed was that he sort of basically had this similar sort of setup with a piston this time. But he changed it slightly. So here's his piston and his gas molecules. But what he did, he was interested in the relationship between the volume and the temperature. So what he did was just have like a little, fire underneath so that the temperature would increase. So the temperature of the gas molecules inside this structure, inside the gas chamber, increased so that the movement of the molecules increased. So we have the same pressure inside and outside. So the pressure inside the piston is the same as the pressure outside the piston. It's the atmospheric pressure. Excuse me. And so what do you think happens to the movement of the molecules when you heat them up? According to the kinetic molecular theory, as we heat up the molecules, are they going to move faster or are they going to move slower?
It would move faster.
Yeah, they're starting to move faster. Anytime we add heat, anytime we add thermal energy to a system, we're also going to increase the kinetic energy of that system too, if there's things in there that can move. And so these molecules start to move faster because they have more energy. So they're moving faster. They're hitting the sides of the container now more frequently. So the pressure would go up, but this piston is allowed to move. There's basically no friction. And so it's able to move up and down. And it maintains the same pressure on one side of the piston and the other side of the piston. So with that being the case, if the pressures have to stay the same, what's going to happen to the volume? I think I compared it to a balloon. Remember, like if you blow up a balloon and then you stick it in liquid nitrogen, it shrinks because the gas molecules are moving much more slowly. And so it shrinks up. But then when you take it out of the liquid nitrogen, which is extremely cold, and you put it back on the table, what happens to it? Providing the rubber doesn't break, of course. What happens to the balloon? Is it going to stay the same size?
Will start getting bigger.
It will. Yeah, it'll start getting bigger. Those molecules will start moving faster and faster. And as they do, they're going to push on the sides of the balloon with more and more force as they're moving faster and faster. Now, the pressure inside the balloon and the pressure outside the balloon in the room is the same. They're both 1 atmosphere. And so the more and more force that the molecules impart to the sides of your balloon, as they start to hit it faster and faster and faster, they start pushing the boundaries of the balloon out further and further and further. So in this particular example, as the temperature goes up, what's going to happen to the volume? Just like the balloon.
Volume's going to go up.
Volume's going to increase too. So as the temperature goes up, the volume also goes up. And this piston is going to be pushed backwards so that a new volume will be established. And if I were to draw the molecules will be further apart, because sort of mentioned at the very beginning when we started talking about gases. Gases will fill any container they're in. That's what makes them unique. We talked about the different states of matter. Liquid won't completely fill a container unless we keep adding liquid to it. And solids, of course, don't completely fill a container until we add more solids to it. But any amount of gas we put in a container will fill it, because they're all moving and they don't interact with each other. And so basically they're just going to fill the container and bounce around. And so there'll be exactly the same number of particles when this container gets bigger. Now here's my new container. So it'll be the same number of particles, but they'll be further apart. And they'll just keep getting further and further and further and further apart until the top pops off. Or the piston is just stopped from moving. And then when the piston stopped from moving and the volume stays constant, what's going to happen to the pressure as we keep increasing the temperature? Let's say we get to a maximum, we get to Vmax, this is like the biggest volume we can form with this particular setup. Once it gets to that maximum volume, what's going to happen to the pressure if we keep increasing the temperature?
Doesn't it stay the same?
No. Think about it. Basically, it would be if I had a container and, I allowed the gas to fill it, and then I stopped filling it, but then I just kept increasing the temperature of the gas inside. So would the pressure eventually start increasing or staying the same or go down?
Increasing?
That's right. Yeah, because once the gas is completely filled, has moved the piston to the very top, there's nowhere else for it to go. It can't expand the volume anymore. And so if I keep increasing the speed of the molecules, and they can't expand the container anymore by pushing on the sides of it, once it can't get any larger, that pressure then is going to start to increase. Which is why when you do this sort of experiment, you've got to be careful that you watch the volume, because once the volume gets to the highest it can possibly go, if we keep increasing the pressure, keep increasing the temperature, then the pressure is going to go up. And then we're no longer looking at the relationship between simply temperature and volume. Then we're looking at the relationship between temperature and pressure. That's not what we're trying to find. So when we do that experiment, we'll have to keep an eye on that. So in this particular instance, because volume goes up as temperature goes up, if we multiplied V1, if we multiplied the initial volume by the initial temperature, that is not going to equal the second volume times the second temperature. This is going to be higher because the temperature's gone up and the volume's gone up. So they don't equal each other. because they're directly related. As they both go up and they both go down together. So I can't multiply them anymore. So what in Charles' law, we see that we divide them. Because then when V1 divided by T1, if I increase my temperature by 2, so if I have 2 times T1 on the bottom, I'll have 2 times V1 on the top. You see how when they're directly related, they both go up and both go down together. So in that instance, if they're inversely related and go up and down together, I can divide them now. And now they will equal each other. Those two will be equal because then I got 2 on the top and 2 on the bottom. And now V1 T1 equals V1 T1. So now we have the same thing. And the same thing would be true if I reduced the volume. So if I have my initial volume and my initial temperature, and then my volume went down by half because my temperature went down by half, you see again that we can just get rid of the 0.5 on the top and the bottom, and we're right back to where we started. So anytime you see two things being multiplied together, that means that they're inversely related. And anytime you divide them, they're directly related. It seems like it should be the other way around. But think about what the effect will be if you change one and the other. If they both go up, you can't multiply them because then the things one side of the equation will just increase tremendously and it won't equal the other side. But if you divide them, they'll stay the same. So let's look at Gay-Lussac's law, or Gay-Lussac's law and Avogadro, because they're pretty much related in the same way that we just talked about. So with Gay-Lussac, he noticed the change between pressure and temperature. Let's just make our good old piston again. So this time, it's locked. And so this volume can't change. Basically, we're just stuck with one volume. And you fill it with N moles of gas. So that is constant. So your amount of gas is constant, your volume is constant. So under those circumstances, when you start heating it, the molecules are going to start moving more quickly. And so here's my initial volume. So and that's going to stay constant. So what's going to happen when I raise the temperature? What's going to happen to the pressure? Is the pressure going to go up or is the pressure going to go down? Now just think about the change. What happens when we change the temperature? What happens to the molecules? So I can increase the temperature, molecules are going to move faster. What's going to happen to the pressure?
Pressure goes up.
Yeah, it does. Pressure goes up too. Because like we talked about, those molecules are now moving faster. When they hit the sides of the container, they can't push on them to make them any bigger. So they're hitting faster and hitting with more and more force. So there's nothing that can happen except the pressure increasing. Because the walls of the containers are going to be hit more frequently. And so the pressure is going to go up. So you can see these two are going to be directly related. And you can see that they're going to be directly related by looking at the law. Because we divide one by the other. And so if I keep putting V, but I really want to put pressure there. So when I have my initial pressure, here's my initial pressure and my initial temperature. If I increase the temperature by 2, so now I'm going to have 2 times the initial temperature. My pressure will also increase by exactly the same amount. So I'll have 2 times the initial pressure. And so you see when we just cross out the 2's, we're left with the same thing on both sides of the equation. And then finally, same thing is true of Avogadro's law. Avogadro did experiments at constant temperature and constant pressure. So basically he was in a lab where the temperature was basically the same. It was around 25 degrees Celsius, so around 298 K. And the pressure was like 1 atmosphere. That wasn't going to change. And he had what we call a eudiometer, which is a fun way to say test tube, and did a reaction with a hose attached that led to the eudiometer. And so he had this hose, and then this was connected to a flask of some kind where he did his experiment. And so when he did an experiment that produced gas, this was filled with water. So this test tube is filled with water. And when gas is produced, it basically bubbles up and pushes the water out and then creates a volume that you can measure. You can measure the volume very accurately. Basically, so it looks like the burette that you guys use for the titration, except there's a rounded top, rounded bottom. You flip it upside down, and you read the volume as it fills up from the top to the bottom. So he noticed that when he did an experiment that produced n moles of gas, he would get a volume. So N1, he would get a volume 1. So then he made a note of what the volume was. Then he filled up the test tube with water again. He did another experiment where he made 2n moles of gas. And then he noticed when he read the volume of gas that it was twice as much. So it was 2 times whatever his initial volume was. And then he did another experiment where he made half the moles of gas and noticed that the volume was half of what it was originally. And so he saw that there was a direct relationship between the moles of gas and the volume of the gas that it took up. And so he saw that there was a direct relationship. Interestingly, and we'll learn about this a little bit later, there was not a relationship between the grams of gas produced or the mass. The mass of the gas produced is not directly related to the volume. Anyone sort of, why would that be, you think? If he did 2 reactions that produced the same number of moles of gas, but one gas had 3 times the molar mass, it didn't matter. The volume was the same. Why do you think that would be? Because if we did it like a precipitation reaction, where we made a solid, and we had 3 times the precipitation, 3 times the mass of the precipitation. Oh dear. We would notice that we would see the mass would directly. We'd look at the precipitate is 3 times as much. It's 3 times the mass. But if our gas is a product, the volume stays the same regardless of the mass. Anyone have any ideas why that would be? Hang on for a sec. I will. Oh, poor guy. No one's got any ideas? Something unique about gas molecules. So what's the difference between gas molecules, liquid molecules, and solid molecules? It's like, what's the, like, sort of the basic difference?
The distance in gas, it's too far.
The distance, exactly. The distance between molecules of a gas are really huge. The distance between liquid molecules come in pretty close contact with each other. And solid molecules are, like, basically by definition, are in constant contact with each other. So what difference do you think that makes? Because of the vast difference in the distance of the molecules. So if I have two heavy gas molecules, are they going to be about the same distance apart as two lighter, with less mass molecules?
Do you mean the pressure in liquid is more than the pressure in gas?
Well, the liquid, when we talk about pressure, we're talking about gas pressure in particular. So yeah, a liquid actually doesn't have any gas pressure. We'll learn later it has a partial pressure. But you get. So basically my question is, do you think large gas molecules and small gas molecules are the same distance apart?
Yeah.
No.
Yes, yeah, they are. And that's why it doesn't matter whether gas molecules are larger or smaller, they take up the same volume because the distance in between them is so great that it doesn't really matter what the mass is. It only matters how many molecules there are. And so that's why it's the moles of gas that dictates what the volume is or what the pressure is, and not the mass of them. And we'll learn this a little bit later when we get to it. We'll learn that basically all gases take up the same volume at 1 atmosphere of pressure. That it doesn't matter what the gas is, with very, very slight changes depending on how well. If those gas molecules interact with each other a little bit more, it'll be a little bit smaller. But generally, everybody interacts with each other pretty much the same, which is not much at all. So we can see that Avogadro's law, because we're dividing them, means they're directly related. So we have 3 where they're directly related and 1 where they're indirectly related. And then when we do our experiment on Wednesday, we're going to see how we can come up with basically a universal law that puts everything together, so that if we know if we know pressure, volume, and moles, we can figure out the temperature. If we know the temperature, the volume, and the pressure, we can figure out the moles. Basically, if we know any 3 things, we can calculate the other thing, because all 4 of those things are related to each other. Okay, so give me about 5 minutes. I got something to deal with here. Some sick dogs, I'm afraid. Go to the simulation and we'll get started there, okay? I'll be back in a sec. Okay, So we got to, the first one we're going to do is Boyle's Law. So the very first question is, since we're dealing with Boyle's Law, which relates pressure to volume, what are we going to have to keep constant?
S should be constant.
Say the gas should be constant?
Yeah.
Yeah, the amount of gas should be, that's right, the amount of gas should be constant. We shouldn't be adding or subtracting any, because that will affect the pressure and the volume. What else needs to be kept constant? So if we're looking at the relationship between pressure and volume, what else? So we need to keep we keep a constant amount of gas. That makes sense. What else do we have to keep constant?
Temperature?
The temperature, right. Because remember, there's four things any experiment involving gas will change: the amount, the volume, the pressure, the temperature. And so anytime you want to look at the relationship between any one of those things, the other two have to be kept the same. So we can look at the direct relationship between just two independent variables, or one dependent variable, one independent variable. We're going to change one and look at the effect of the other. So everything else has to stay the same so it doesn't mess up our experiment. So in this instance, what we're going to do is take all the gas out. You remember how we did that? Just below the pressure valve, there's like this little handle. And when we click on it, it basically lets all the gas out. And notice when we let there's no gas, there's no pressure. Also, no volume, but there is a child. So what we do is that we basically add gas back, and we'll add a constant amount. So let's put a couple of pumps in there. One, oh, wait a minute. Keep the other way. So yeah, 1, 2. Here we go. So right now we take a note of the temperature, and we can keep this temperature, or you can change it to a different temperature. We can lower it if we want to. Can lower it to like whatever we want. And then just look at the changes of volume. I think it was around 320 or so. So what I'm going to do is I'm going to increase the volume to 1,000. So then I make a note. I have the three things that I'm measuring. I put in a constant amount of gas. I check the temperature, and I'm not going to change it now. So basically, I'm doing my experiment at 320 K. And I look at the volume, and it's 1,000 liters. And we know that's the maximum. The piston's at the very top. It can't get any higher. And we make a note of the pressure, 1.58 atmospheres. So now I'm just going to reduce the volume. And so what I'll do is see what the lowest level is. And you see the little lock to the side, that's when we want to keep the volume constant as well. But in this instance, we're changing the volume and seeing the effect on pressure. And so which one is our independent variable and which one is our dependent variable for this experiment? And better question, do you know what the independent variable is? What does that mean?
That is affected by other.
One more time.
That is, will it change depend on the other thing change.
So is that so the independent variable changes as you change the other one, the dependent
Yeah.
variable?
Yeah.
Okay. Okay. Does everyone agree with that? It's the other way around. I know it seems like that should be, right? I mean, it makes sense that way. But think of it this way. The dependent variable depends on the independent variable.
Mhm.
The independent variable is the one that we are independently varying. So, I as a researcher, I can change something in my experiment. I can add more reagents. I can change the temperature. I can change the volume. I can change all sorts of things. What I can't change is the outcome of the experiment. That's just going to happen. But the outcome is going to be dependent on what I do. So if I change the temperature, let's say if I'm doing a reaction and I increase the temperature of the vessel that I'm doing the reaction in, that's going to have some effect on the reaction. It's probably going to go faster. Like, 90 times out of 100, that reaction is going to go faster. But I don't know what the effect is going to be until I do the reaction. So I independently varied what the temperature is. Now the effect is dependent on whatever I change the temperature to. So in this particular, so which one is dependent? So I'm looking at the relationship between volume and pressure. So which one is the independent variable and which one's the dependent variable? Which one are we changing? And what is dependent on the thing we change?
Independent is temperature and the pressure is the dependent variable.
Oh, but we're not changing temperature. I'm gonna lock it in. That's gonna be constant for this experiment. And you can make the temperature whatever you want, but once you start the experiment, that's got to stay the same. So that's constant. That won't be changed. But you are going to change something and look at the effect on the other.
Are we changing the volume?
Yeah, we're changing the volume. We're going to either press on the low button and we're going to change the volume, and then we're going to see what the effect on the pressure is. So the volume
It's independent.
is independent. So this is our independent variable. And the pressure is the dependent variable. So when we plot this, Cammie, so when we plot this, which one is going to be on the x-axis and which one is going to be on the y-axis?
X-axis is the volume.
That's right, because we put the dependent, as we change x, we want to see what the effect is on y.
Y is the pressure.
Y is the pressure, exactly. So I've selected a temperature, got my volume. So first I see what the volume is. I see what the pressure is at the maximum volume. So I make the volume as maximum as possible. I notice it was 1.58. Now I'll see what the minimum volume is. I think it's 150, but I'm not sure. I'm gonna keep going all the way down. Yeah, 150 is as low as we can go. So I'm going to make a note of that. So at 150 liters, my pressure is 1050. Then I want to pick 3 or 4 other volumes that are in between those two, so I can get a nice spread on my graph. I don't want to have too many points. So when I graph it, I want to show you a little something. When I graph it, when I'm plotting my graph, so when I've got my volume here and my pressure here, I don't want to have too many points. I don't want to have too many points close together, because if we want to see whether this relationship is linear or not. And so if I have too many points that are really, really close together, I can't really say if this is going to, if it's just linear in that one particular place, but then will flatten out, or does it look like, this? I won't know because all my points are really, really close together. So what I want to do is stretch it out as far as I can. So I get the minimum and the maximum, and then some points in between. That will give me a better idea of whether a line can connect all those dots. Because if I have them too close, there's a whole lot of lines that can connect a whole bunch of points that are really, really close together. But when they're really, really far apart, then I feel more comfortable saying that a straight line can actually connect all those dots. When I have points on one end of the line and points on the other end of the line. If they're all close to one side of the line or the other, I can't really say. So we've got our two maximums. We got 1,000 and we got 150. So then we'll just pick like 4 in between. So 150, I'll go up to say that. That's a problem. You got to click on it and then click it again. So like, yeah, so the 270, I've got 5.84. Remember, we do not touch the temperature. 390, I've got 4.04. 560, I've got 2.81. And 780. And of course, your results are going to be different than mine. You've probably got different volumes. 202. Okay. And since it's so easy to get data points, you can collect as many as you like. I would recommend at least 5 or 6, but you can have 8, you can have 10 if you like, because it's not like it takes you a whole lot more time to do the experiment. The other thing to notice is as I change the volume, what happens to remember over on the side, we have 2 things we're measuring on the side. People remember what those were? I've got KE and RMS. Do you remember what those were? What does the KE stand for?
Is it kinetic energy?
Very much is. Yeah, it's the kinetic energy. Kinetic being movement. It's basically how much energy, the average energy that those gas molecules have moving around. And notice as I change the volume, does that change? I'm changing the volume, the pressure's changing. Does the KE change at all?
No.
Doesn't, right? And the RMS, basically, that's the average speed. It gives you sort of the speed that the molecules are moving in meters per second. That doesn't change either. So what do you think the kinetic energy is actually dependent on? It's not dependent on the pressure. It's not dependent on the volume. What's it dependent on? I could even put another pump of gas in. I'll put another pump of gas in. So see if it's dependent on the number of molecules. I put more molecules in. Has that changed? So now there's more gas in there than there was before. Are they moving any faster? I'll put more gas in. Has the energy of the molecules changed at all?
No.
So we've learned that the energy of the molecules does not depend on the volume. It does not depend on the pressure. It does not depend on the amount of gas. So what's the final thing that it must be dependent on? Only one thing left when you're dealing with gases. So if I change the volume, no effect. Change the pressure, no effect. Change the amount of gas, no effect.
Temperature?
What is it? The
Temperature?
temperature. That's right. The temperature is the only other thing I can change. And remember, temperature is thermal energy. So if I add more heat, watch what happens.
Move
It goes,
faster?
they're moving faster, right? The amount of kinetic energy has gone up. The root mean speed, the average speed has gone up. And my volume has also gone up because now those molecules are moving faster. They're hitting the sides of the container more frequently. They're hitting the piston with more force and they're pushing it up. So let's do our first graph because we have some data. We've collected some data and let's see how we would deal with it. So I'm going to share. So you guys want to look at, you're going to do Excel or you're going to do Google? You guys going to be using Google Sheets or are you going to be using Excel? Most people are going to be using Google, I understand. Is that how you're going to do your graphing?
I'll do Google.
But you can use, if you have Excel, I mean, it's awful, but I mean, they're both fairly awful. But we can have a look at both. It just depends on, because I thought last week most people were using Google Sheets. Is that true?
I can use either.
Okay. Okay, why don't we look at Google Sheets then? I mean, because everybody can use that. And if you know how to use Google Sheets, presumably you know how to use Excel as well. So I'm going to share. All right. So I'm going to get rid of this and put my temperature, my pressures in. Oh, wait a minute. No, my volumes and my pressures. Here we go. So I'm going to change that to volume. Now, in your data table, you should have units. You should always have units in your data table. So for volume, I would put liters. And for pressure, I would put atmospheres, because that's the units we're dealing with. So my initial volume was 1,000, and my pressure was 1.58. And then I had 150, and my pressure was 10.5. And then at 270, I had 5.84. And then at 390. Does everyone see the sheet I'm working on?
Yeah, I can see it.
All right, cool. Okay. 4.04. At 560, I had 2.81. And at 780, I had 2.02. Okay. So the plot I want a scatter plot. Basically, I don't want a line plot. I just want a scatter plot. They'll just put the points wherever they go, and without trying to fit any particular relationship to them. So just highlight them, and then go to Insert. Is that correct? I think that's right. And Chart. And it'll ask you, what kind of chart do you want? You want a line chart, you want a bar graph, whatever. I want a scatter chart. Okay, I'm gonna move this over a little bit. Now, I also want the relationship here. So you can see I've got volume on the bottom and I've got pressure on the side. So that's good. My volume is my independent variable. Now, as I'm looking at this, does that look linear to you?
Oh,
Kind of.
No.
Well, let's fit it. Let's go to customize and grid lines. No, I want. Where's grid? No, I want to fit a trend line. Where's my trend line? Series. Yes, series. Yeah. So series. Click on series. Go to trend line. And it'll ask you what kind of line do you want. Say I want a linear line. And say show the R squared. Anyone remember what the R squared is? The R squared refers to the fit of my line. So do I want a high R squared or do I want a low R squared?
It might be lower because the point under the line.
Sorry?
You said it might be lower because the point is under the line.
What might be lower? No, what are you saying is lower?
This point, the one we have, it's below the line, the one we have in the graph.
So that's the best fit for a linear, that's the best fit the computer can come up with for those points. So the R squared tells you how good that fit is. And you want as close to 1 as you can get, because basically what the R squared is it's measuring the distance, excuse me, the distance between your points and the line. And so if there's no distance at all, basically the fit is a perfect 1. And the further and further those points get away from the line, the less and less R squared becomes. And so what's happening here is that it looks like linear relationship really isn't very good. And so what have we done? How can we increase this? Oh, we also want the trend line. Do you remember how we get to show the equation? Oh, data labels. Is that it? No. We want
Click on custom.
on legend, right? There it is. Nope. Yeah, we're charting. Oh,
It should be under
titles.
series. It should be
It's under series.
yeah, and then under trend line, and then click on
The
custom.
label.
Yeah.
Use equation. There it is. Yeah, so this will give us the equation, the y equals mx plus b equation. So why isn't this linear? Basically, what's the relationship between volume and pressure? Is it direct or is it indirect? So the fit of my line is y equals mx. And so this is my pressure is some some slope times my volume. So is there a direct relationship between volume and pressure? Or is it an indirect relationship? What if we plotted the inverse of the pressure? You think that would help us? Let's try doing that. So does this work the same way? Next time I just put equals 1 over C3. Yeah, let me just drag it down. Let me just drag it down. All right. So now I've got 1 over P. Everyone see how I did that? So it would be 1 over atmospheres. Everyone see how I did that? How I was able to divide all of them at the same time? Have you used that before?
You demonstrate again, please.
Sure. I'm going to get rid of it. I'm going to move this over to the side. Oh. That over there. All right, so to get that, I just click the box where I want it to start. I just put equals 1 divided by, and then basically what I'll do is figure out where my data is that I want to change. And I see the first one I want to change is at C3. I just type in 1 divided by C3, and it will calculate it for me, so I don't have to calculate it. So I'm going to put 1 over C3 and just hit enter. And it'll do that. Oops. Okay. So there it is. 1 over C3. So then you see it's got this little dot, a little square dot on the bottom right-hand corner. And just click on that and drag it down. And it basically does that same calculation for all the other numbers in that column, okay? So now what I want to do is plot volume versus 1 over P, rather than volume versus pressure. So I'll just select those two columns. Go back to insert, chart. Don't want a bar graph. I want right, I want a, where is it? Where's my scatter plot? How come I can't do a scatter plot this time? Oh, there it is. Okay, scatter. Okay, now I'm going to do scatter plot. Right, let me erase this stuff. All right, so this time I'm plotting volume versus 1 over the pressure. Okay, so I've got volume on the bottom, it's my x-axis, that's because that's what I'm changing, that's dependent. And on the side, I've got the inverse of the pressure. So now I'm going to see what the relationship is between them, see if that's linear or not. Let's go down to customize, series. I want the trend line. I want to show the R squared. And I want to see my oh no, I want to see the equation. Damn it, where's my equation again? Undercut. Oh, label, there it is. Use equation. Okay, get rid of that. So I'm going to put the two graphs side by side so you can see them. So that's when so the one on the right is when we plotted pressure versus volume. And the second one is where we plotted the inverse of pressure versus volume. Have a look at the difference. So what does the plot on the left tell you? Which one's linear, basically?
The one on the left.
Yeah, the one on the left, clearly, right? Because I mean, look at the R squared. The R squared is perfect. It's exactly 1. You can't get more you can't get a better fit than that. And look at all the points, they fall exactly on the line. And if all your points fall exactly on the line, your R squared is going to be 1. Because there's no change between where the point is and where the line is. So it doesn't decrease from 1. So what we can do is basically see what our relationship is between volume and temperature, or sorry, between pressure and volume. And so that comes from our y equals mx plus b. And that is how we put this this particular equation right here. That's how a linear equation is expressed. So this is your slope. So the slope is 6.33 times 10 to the minus 4. And B is where it hits the y-axis. And we see that hits the y-axis at 5.84 times 10 to the minus 4. So pretty close to 0, which is what we would expect. Because as the pressure goes to 0, the volume goes to 0. So it should be pretty close to 0. And that would be how much, that's the effect of the volume on the pressure, okay?
Professor,
Yeah.
so in the lab report, did you want us to put both graphs or just the one with the linear?
Yeah, figure out which one is going to be linear, and you want to post that one. Yeah, so it would be the one on the left is the one you're going to be posting this one. So what I'd like to see is the data table with as many points as you can, and you could just copy and paste the data table and the graph and just paste them right into your report. You don't have to write them out again. Just make sure you have, the other thing we want to do is make sure that you have a title for the graph. So what I would do, I would change this to make sure, you know, I have something like Charles or Boyle's law. At 320K. Because you want to, I want to know what's the experiment. I want to know what you've, what things you're keeping constant, and what are the effects of the two other things. So show me show me the plot, give the R squared and the equation. Okay. And I think you'll see when two things are directly related, you're going to want to plot 1 over versus one over the dependent variable versus the dependent. And when things are inversely related, you can just plot one versus the other. If you don't believe me, try it try it out. But you can see that's what happened here. So this one's indirectly related. I'm sorry, it's the other way around. Obviously, I didn't have enough tea. These two are indirectly related, right? So as one went down, the other one went up. So as my volume went down, the pressure went up. So if I plot them one directly against the other, it's not going to be a straight line. When they're directly related, if my x goes up by 2, my y goes up by 2, my x goes up by 3, my y goes up by 3, that's a straight line. Sorry, I confused myself there for a minute. But these two are indirectly related. As one goes up, the other goes down. So that's not a linear relationship. So we can't make a linear plot of that. That would be, if we were to actually fit that, so if we look at the plot on the right, if we were to fit that to a line, it would look like this, right? That's logarithmic. So that if we plotted that to a logarithmic fit, we would get much better than R squared of 0.74. So yeah, so if they're directly related, we do this kind of plot because they're direct, and if they're indirectly related, we do 1 over, because that's what indirectly related means, right? It means the numerator is related to the denominator of the other one. So let's do one more, and then I think you can probably figure it out. Okay. So does everyone? We'll do one more. We'll see how to use the simulator once more, and then we'll come back and we'll do both the plots. Does that sound good? Anyone have any? First, did anyone have any questions on the plotting, direct versus indirect relationships? Let me clear all that out so you can see something.
I just have a general question for the lab report.
Sure.
Just to clarify, we just need to post the graph and not like the data table or anything like
Both.
that. Okay.
Both. Always, if you have a graph, you have to have a data table to show what the numbers are, because I won't know just by looking at this. I'm looking at this graph right here. I don't know exactly what that point is. I know it's somewhere around, I don't know, 550 liters or something. I don't know exactly what it is. So if I want to recreate that graph to see if like that truly is the relationship between them, I can't do it because I don't know what they are. But if you give me your actual data, I can recreate that and see, well, is this actually, you know, is this correct? And then, okay, yes, it is. So yeah, whenever you publish anything that has data, that has a graph in there, you have to have the original data as well, so that the reader can check for themselves.
Okay, thank you.
Yep, no worries.
Just to clarify, when it's indirectly related, you have to
Mhm.
divide 1 over that pressure to get it to be linear, right?
Right, because if it's indirectly related, what indirectly related really means is that the numerator of one of my variables is actually related to the denominator of the other one. That's what indirectly means. It means that the numerator changes the denominator of the other one over the other one. That's what indirect means. So as my numerator goes up, my denominator also goes up, meaning that my 1 over gets smaller and smaller. So as one goes up, the other one goes down. So if I have 4 over up on top and 4 on the bottom, that means 4 more, and this means 1/4, right? So as this is getting bigger, this is getting smaller. So indirect means I'm plotting 1 over. I'm plotting my independent variable is going to be related to 1 over my dependent variable. Okay, so it just means I'm changing the denominator of the other one, not the numerator. So my numerator of volume is changing 1 over the denominator of my independent variable. And so if you forget and you get something that looks like this, if your r squared is like not close to 1, then that basically tells you like, oh, that's not a linear relationship. It's indirect. Oh, right, I need to flip it. But yeah, but just for future reference, that's what an indirect relationship means. Numerator versus denominator. If it's direct, that means the two numerators are related to each other. Does that make sense? I'm quite sure I don't think I'm even making sense to myself anymore. So I get off of these tangents. But yeah, just look and see if it's direct. If it's direct, the two directly influence each other. If it's indirect, just think you got to flip it around because it's indirect. All right, let's go back to our simulator, see how it's doing. Should be just sitting there simulating. Yep, still simulating. So let's do the next one. We'll go to the next one is Charles' law. Now, Charles' law, remember, we're changing the temperature and we're seeing the effect on volume. So we're going to keep the pressure should stay constant and the volume should vary. So let's go back and empty. I put a lot of gas in there, so let's empty it out. Man, that was a lot. So we should find what our maximum and minimum are. So let's put one pump in there. And then change. So again, 150 is our lowest. Cool this down because we're going to be changing the temperature quite a lot. So I think our minimum is 10. So that's our minimum temperature and our maximum. So at 10, So at 10K, at 0.16 atmospheres, our volume is 150. And see what we get to 1,000. Oh. Yeah, it's tough to get a constant temperature. There we go. Oh, it seems like we need a particular pressure for the volume to change. Now we're just seeing the effect on pressure. It shouldn't be doing that. Oh, right, we need to decrease the temperature. Sorry about that. I should actually follow my own instructions. So let's start over. All right. So in the instructions, we're going to put 2 pumps of A in. So gas A. 1, 2. And then lower the volume to 500 liters or thereabouts. Then we lower the temperature. So let's make a note. So we have 530 liters, 5.57 atmospheres, and 600 Kelvin. So we make a note of all that. And then we just reduce the temperature by about 100 or so. Right, so at 510 Kelvin, pressure's the same. That's important we keep the same pressure because we want to keep the pressure constant. And our new volume is 451 liters, okay? And we just cool it down some more by about another 100 or so. So at 425, pressure's still the same. And it's important, keep an eye on the pressure. We don't want that to change because we're looking at the relationship between temperature and volume. We don't want the pressure to change. So at 425, we have a volume of 375. Then cool it some more. So at 345, my volume's 305. I'm keeping, and I'm making notes that my pressure has not changed. That's important. So cool it off some more. So now I'm down to 265. Pressure's still the same. And I'm at 234 liters. So 175K. Pressure's still good. And I'm at 155. And I don't think I can, I think the volume will just lock in at 150. Let's see. Yeah. Yeah, notice this time. So I lowered the temperature from 155 to 110. What happened to the pressure? My pressure before was 5.57 atmospheres. I lowered the temperature some more, and what happened to the pressure?
Lowered.
It went down. How come? It stayed the same all the way through. How come it went down this time? So two questions. How come it went down this time? And can we use this point in our experiment when we graph it?
Is it because temperature and pressure are directly proportional, and so since you lower temperature, the pressure will also go down?
No, the pressure stayed the same all the way from 600 K all the way down to 175 K. They were directly related. I mean, the pressure stayed constant, but now it went down. Why is that? What about the volume? What happened to the volume? Because my last volume at 175 K, my volume was 155 liters. See what the volume is now. Now, if I lower the temperature even more, watch what happens. What happened to the volume?
The volume stayed the same.
Mm-hmm. And what happened to the pressure?
It goes down.
It went down, right? So how come the pressure kept going down? Once we got to a certain temperature, then the pressure started dropping. Why is that? It was fine all the way till it got to around 150 liters. Now the pressure's dropping.
When the temperature goes down and the pressure goes down, the molecules will slowly move.
Yeah, they're moving more slowly, but they were moving more slowly before too. Every time we dropped the temperature, the molecules started moving more slowly. But something happened when we got to around 150 liters of volume. What happened? We started at 530 liters, then it went down and down and down and down till it got to 150, then it stopped. Basically, the volume stopped decreasing. There seems to be no way we can reduce the volume below 150 liters. So once we got to 150 liters, then the volume stopped being variable. Now the volume's constant. And we know that when the volume is constant and we reduce the temperature, the pressure starts to go down. So basically what happened is that like midway through the experiment, the things we were keeping constant stopped being constant. So my question is, can we use this particular point, and can we put it on our graph for when we're plotting the relationship between temperature and volume? Can I use 65 K is related to 150 liters of volume? I'll lower it some more. Now it's a 30 K. Still have 150 liters of volume. Can I use this point in our graph? What do you think? Can I plot all of these points? It's either yes or no. Someone take a stab at it.
No,
No, that's correct. How come?
because it's not going to be accurate.
That's true. Why isn't it going to be accurate any? Why is it not accurate once the volume stops at 150? That's what I mentioned a minute ago. Remember, when something is, we're keeping one thing constant, and then something else started being constant.
Pressure needs to be constant.
Exactly. Right. Yeah, we can't include these points because the pressure is no longer constant. And when the pressure is not constant, we're no longer looking at the relationship between only the volume and the temperature. Now we're looking at the relationship between the temperature and the pressure. And that's not what we're investigating. So basically, we're limited for data points greater than a volume of 150. And so when you do this experiment on your own, whatever you choose as your starting volume has to be less than 1,000 because that's the maximum. So, and it's got to be more than 150 because that's the minimum. And it's that range of volume is the only place where we can keep the pressure constant. Because once we go above 1,000, the pressure's going to start to go up with temperature. And once we go below 150, because we're cooling things down, the pressure's going to go below whatever it was we started with. So it has to be in the area where the pressure is exactly the same. So once the pressure changes, we're no longer looking at the relationship between temperature and volume. We're looking at something else. So we can't include those points. So basically what I've got here is 1, 2, 3, 4, 5, 6. I got 6 points between 530 liters and 155. So, and the pressure's the same in all of them. So we're going to use those. Okay, is everyone clear as to why that would be? Why you have to keep the volume between 150 and 1,000? It's basically, it's the only place where the piston can freely move. And the piston is only free to move when the pressure is constant, because it will move because the pressure in the system is the same as the pressure outside of it. It'll move up and down. The volume will keep the pressure the same inside the cylinder and outside the cylinder. Once we get to the top, the pressure is going to increase inside the cylinder and be more than the pressure outside. And when the piston gets all the way to the bottom, the pressure will be lower inside the cylinder than outside. And so we can't look at above the maximum or below the minimum. The volume has to be in between. Is that clear as to why that is? We don't want to have two variables changing at the same time. We only want one changing at a time. Yes, no? I've lost everybody again. Actually, why don't I include this point and we'll see. So I've got 30K. Oh, wait a minute. 30K and 150. And I'll get the other, so I'll heat it up a little. So, and 55K and 150. So we'll put those points on the line and we'll take them off and we'll see what difference they make, okay? So let's go plot all our data. Go back to the spreadsheet. New sheet. And hopefully this won't drop out while we're, okay, good. All right, so is this a direct or indirect relationship between temperature and volume?
Direct.
Direct, right. So we're going to plot temperature in K versus volume in liters. So am I going to just do one versus the other? So am I going to plot temperature versus volume or temperature versus 1 over volume? Because it's direct. What do you think? Am I good? Oops, other way around. Let's put the data in. You guys can decide whether I'm going to plot K versus V, or I'm sorry, T versus V or T versus 1 over V. So has anyone figured out whether it's going to be temperature versus volume or temperature versus 1 over volume? Oops. 55 versus 150. 30 versus 150. Okay. All right, so here's my data. I got my temperatures on the left and I got my volumes on the right. So am I going to plot them directly or do I need to calculate 1 over volume? Actually, I can just do that. We can see. Equals 1 divided by E3. Right, so 1 over V. So which of these is going to be linear? 1 over liters. Which one's going to be linear? Temperature versus volume or temperature versus 1 over volume? This is a direct relationship.
Temperature versus volume.
That's right. That's right, because the effect of the temperature is direct to the volume. So if I change the temperature by 0.75, the volume changes by 0.75. If I change the temperature by 0.5, the volume changes by 0.5. It's direct. One has a direct effect on the other. So to prove that, let's plot them. So insert chart. Here we go. I don't want a column chart. Thank you. Scatter. I want the trend line. And I want the R squared. Oh, wait a minute. And I'd like to see the equation. Label, here we go. Use equation. Okay. So let's have a look at, move this out of the way. Let's have a look at the plot. So our R squared isn't bad. I mean, if I was just throwing like random data points together and looking at their relationship, and I saw an R squared of 0.95, that's good. That's actually good. But if we look a little closer, I think we see a pattern here, right? Anybody see it? There seems to be something different about these points and these points. What's the difference? So these were my points between 600 liters and 155. And then those were when my volume was stuck at 150 and my pressure went down. What do you notice about those two sets of points? Nobody sees anything. Come on, there's got to be some scientists in the bunch here. What do you see? Scientists are trained to notice patterns. That's our whole job, is to look for patterns. You see a pattern on one side of the graph and the other side. Two on the left side don't look different to anyone? Really? Nobody sees any difference? All right, let me do this. Do you think I could draw a straight line between all the points on the right side of the graph? If I took out these 2 points here, you think I could draw a straight line between all the rest of them?
Yeah.
Yeah, I think so, don't you think? That looks pretty straight to me. In fact, that looks perfectly straight. So there's something different. These points appear to show a direct relationship between temperature and volume. Those points don't. See if we draw a straight line, see if we draw the red line as straight, and then these 2 points over here are even further off of that straight line. Why is that? How come these 2 points are different? The 2 points on the left, they seem to be different than the rest of them. What's changed?
The 2 points on the left are the volume is constant in both of them.
Mm-hmm. What else? Yes, the volume is constant. What else? So that is true for both of them. Something else is true too. There's something in common with the 2 points on the left that's different from all the points on the right. Yeah, the clue to that is, yes, the volume stayed constant for the 2 points on the left. So what else is also true because of that? So those 2 on the left, they have different temperatures. These 2 points here have different temperatures, but their volumes are the same. So something changed. Those 2 points have a different something, but their volumes are the same. As the temperature went down, what else went down?
The pressure went down.
There you go. Yeah, the pressure for these 2 points, is different than the pressure for these 6. And so that straight line for the 6 points on the right tell us there's a direct relationship between volume and temperature at a constant pressure. When the pressure changes, it's no longer a direct relationship. Now, those points are off the line because we're not looking at the constant pressure anymore. And so we can't use those 2 points because they're taken under different circumstances than the other 6. And so watch what happens. So notice we had our R squared was 0.948. So what happens when we just do a graph of the first 6? Oh, wait a minute. I want. Damn it. There's the scatter. Okay. I'll move that over here and get my customize series trend line and show R squared. Okay, now. So now we've taken these 2 points off. We've removed those 2 points because these 6 were at P1 and these 2 were at P2. So now we've removed them. And look, what's the R squared now?
One.
Yeah, it's exactly 1. And all these points fall exactly on the line, which means that there's a perfect direct relationship between the temperature and the volume at constant pressure. When we change the pressure, that is no longer true. Okay, so when you do this experiment, start at less than 1,000 liters of volume. So you start below the maximum and you reduce the temperature till you get to around 150, but don't go below it because then you're in an area of either above 1,000 or below 150 liters where the pressure will now be different. And as soon as the pressure changes, that relationship between a temperature and volume goes away because now we're changing the pressure. The temperature is affecting the pressure. It's no longer affecting the volume. And so we can only use the points where the pressure is constant. So it's either that, so we either need to use this pressure, and even these 2 pressures here, they're both different. So we can't use either one of them. So only when the pressure is constant, okay? Does that make sense to everybody?
Yeah. Do you want us to add the 2 points where the pressure isn't constant?
Well, what I would do is, yeah, I mean, just you can do it for yourself. Just, take as many points as you want. And you can visually see, I think, when you look at them. I mean, because you should be writing on your notes or something. The volume, the temperature, and the pressure. And so when the pressure changes, don't include that don't include that point. I mean, that's, while I was doing the experiment here, I made notes. I mean, that's what your scientist does. They make notes, right? So I made a note of the pressure, the temperature, and the volume. And so when the pressure was no longer the same, I knew I can't use those points anymore. And you can prove it to yourself. I mean, you could see where the line, where all the points are exactly linear, and then where they aren't. Yeah, so I wouldn't include those. And you can see for yourself which ones to leave off. Yeah, so in this instance, I would write in my, so I've got my units, I got my, I'm changing temperature and what the units are, Kelvin, volume, liters, that's all good. But over here, I want to change that to Charles' law. Not Charles, Charles' law. And P equals, in my instance, it was 5.57 atmospheres. So that tells me, that the pressure for all these points was that particular pressure. Your pressure is going to be, I don't know, whatever it is. But yes, you just pick a, I don't know why I said 500 liters. You could make it, I don't know, 600 or 700, whatever it is. Just make sure your pressure is above 1, and like it's not above 10, because that's the maximum pressure. So your pressure could actually be like 15 or something, but it will only show 10. So so your pressure has to be somewhere in the linear range too. I think it's between 1 and 10 atmospheres. All right, so so the next one would just be looking at the relationship between temperature and pressure. That one's even easier to do, because all you need to do for that one, let me just go back and clear this off. All you need to do for that one is to put some gas in and just lock the volume. So when you hit this, let me take it out to like, get it some volume, it doesn't matter what the volume is. And then hit that lock. Now, when I raise the temperature, the volume stays the same and only the pressure goes up, okay? So then you make a note, at 55 K, the pressure is 0.38 atmospheres. And then as I increase the temperature, remember the temperature will only go to 600. So take readings until the pressure gets to 10. Either your temperature is going to get to 600 or your pressure is going to get to 10. Whichever one comes first, that's when you basically have to stop, okay? And just keep measuring them. And I think, yeah, once it gets to 600, you can't raise it anymore. So yeah, just make a note of what volumes you can use, how many, you can put more pumps of gas in there if you want, and then just go back and repeat the experiment. Like if you wanted to put 2 pumps in, see the pressure goes up, and then you can cool that down. But yeah, don't exceed 10 atmospheres of pressure. And don't exceed 600 K, because you can't, basically. So here's a question. Before we go, I want to put, because there's instructions for how to do the Gay-Lussac law, and then you have to come up with your own instructions for doing Avogadro's law. So you're basically going to be plotting number of pumps of gas versus pressure. Or is it versus volume? Which one is it? Volume. So you're going to be doing N for like moles of gas, for like pumps of gas, and versus the volume. So you'll have to figure out how to do that and get a linear response. But before we go, I want to do one other thing. So you get a temperature here. So I'm going to remove all the gas. Now I'm going to put 3 pumps of A, and we'll see what the pressure is. So at 1,000 liters at 275, the pressure of 3 pumps of A is 2.03 atmospheres. Now, when I empty it, and instead put gas B in, and gas B is bigger. Gas B is a greater mass than gas A. I'll put 3 pumps of gas B in. What do you think the pressure is going to be? You get 3, it's either going to be higher, it's going to be lower, or it's going to be the same. Who wants to make the first guess?
Would it be the same?
Okay, that's a good one. Anybody else want to? So it's going to be higher, lower, or the same. So we get 1 vote for the same. I got my big gas B and my little gas A. And it was what, 203 atmospheres, I think. So we have 1 vote for the same. Who else wants to vote? Can't go with just 1 vote. Come on.
It is the same.
Okay, you got 2 for the same. You know, B looks a lot bigger than A. Anybody else? B is almost freakishly big compared to A. What do you think? Oh, there's 17 of you here. I only got 2 votes. Come on, I need to have at least 2 more.
The same.
Oh man, everyone's hopping on the bandwagon. You're going to be so embarrassed when you're all wrong. Anybody else want to take a guess? Man, no one thinks outside the box. How are we going to discover anything? Think all the great scientists just did what everybody else did? No, they thought for themselves. 1 more vote. What do you think? Bigger molecule, pressure's going to be higher. Okay, I'm going to vote for that one. Anybody else want to vote with me? Remember, bigger molecule. It's going to hit the side of the wall harder because of more mass, right? So the pressure is going to be higher. Nobody wants to agree with me? All right, fine. I'll just be right all by myself. Okay, so we're going to put 3 pumps of big B in there. See what happens. 1, 2, 3. Well, look at that. The pressure is exactly the same. So why do you think that is? We sort of talked about it a little bit before. Why do you think the size of the gas molecule is independent of the pressure? Why do you think that is? But if you look, I mean, obviously for effect, these gas molecules are enormous. So you can actually see them, right? But in an actual gas cylinder, how much of the space inside a gas cylinder is actually empty? And there's no molecules at all.
The cylinder will always be full, right?
Right, it'll always be full, but at the same time, how much of the space in that cylinder will have empty space versus gas molecules? Sort of like an atom, right? If we look at an atom, remember Rutherford's experiment, right? So we have an atom with a nucleus, and then it's, you know, and then electrons around the outside of it. But what's the vast part of the atom is what? It's empty space, right? Remember when Rutherford shot positive particles at it, the vast majority of them just went right through. So when we look at the gas tank, you think most of the space inside is empty or has gas molecules? Like, I think like relatively. What's the distance? Basically, what's the distance between the gas molecules? Small or is it large?
Large?
Yeah, it's very large. There's a huge distance between, like the size of the amount of, if you think of the size of the gas molecules, these little gas particles, versus the distance in between them. The distance in between them is much bigger than the actual gas molecules themselves. And so it's weird to think that we can both have a gas cylinder that's both full and empty at the same time. I mean, like I said before, it's always full because there's going to be, if you take a sample of any part of the cylinder, it's going to be gas molecules in there. But the vast majority of the space inside there is nothing in it because the gas molecules are so small. So if you make the gas molecules slightly bigger, the distance between them stays the same and is the vast part of the space inside the cylinder. So if you change the mass of the gas molecule, the size of them changes so little in comparison to the vast distance between them that has no effect on the pressure or the volume at all, because it's really mostly empty space with the occasional gas molecule zipping by. So that's why the mass of it really doesn't matter. Okay? It's a lot to take in. It's empty and it's full at the same time. Well, you guys did quantum mechanics already, so you know, it's a wave, it's a particle, it's a wave, it's a particle. No, it's both. Yeah, same is true with gases. It's both full and empty at the same time. So you think you guys can, any questions? Because you guys, the instructions for Gay-Lussac's law are pretty much are there for you. And you have to figure out the last one, the Avogadro's law, for yourself. Just remember to keep the, select the temperature so the pressure stays between 1 and 10 and the volume doesn't, no, it's pressure. It's pressure you're going to want to do. Yeah, so yeah, figure out a way to do the Avogadro. It's going to be a little tricky. If you have trouble with it, let me know, and we could maybe do a workaround or something. May not be able to get as many points. Any questions? So you guys are good with the plotting? Show the data table and just copy and paste the data table with the plot next to it. Just put that in your report and label the axes. Label the axes of your graphs. That's really important. So we want the labels present. We want the R squared. It's not super necessary to show the mx plus b to show the slope. It'd be nice if you did that. It's more important to see what the relationship is, whether you can definitely prove it's linear or whether it's some other shape. And then remember to include what you kept constant. So if you did temperature versus volume, what was your pressure the whole time? If you did temperature versus pressure, what was your volume the whole time? That sort of thing.